What I want to talk about today is quite philosophical. And sometimes I have a challenge talking to young engineers. Uh, uh, the criticism is what you say is so abstract. And sometimes it is. Sometimes it's very concrete, but sometimes principles don't have obvious application. And I understand that, but at the same time, abstraction gives us leverage, and we can approach problems that would be intractable if we were swimming in a sea of details. So that's what I'm going to talk about today is a particular set of principles around software design. In particular, I was reading John Osterhout's A Philosophy of Software Design and realized that there's a fundamental difference in philosophy between that approach and the approach that I've been uh, uh, pursuing for the past, okay, so 17 years. So in 2005, I was asked to be on a panel with Ed Jordan and Larry Constantine to celebrate the 25th anniversary of the publication of their book, Structured Design. And that book introduced the terms coupling and cohesion to the world. And those terms, coupling and cohesion, were derived from an analysis of many projects at IBM. They wanted to answer the question, some projects seem to be expensive to maintain and other projects seem to be cheap to maintain. Are there any properties in common between the expensive projects, and are there any properties in common between the relatively easy to maintain projects? And what they derived from those experiences were these terms coupling and cohesion. Now, since then, those terms have come to kind of dissipate and mean a lot of different things. But the original publication, the book Structured Design, had very precise definitions of those two terms. Okay, so I had structured design as a college textbook back in 1400 years ago, but of course that meant I hadn't really read the book. So I thought if I'm going to be on a panel with these guys, I'd better read the book. And so at that point I'd been programming professionally for 20 some years, thought I knew a lot about design, was confident in my skills to design software. So I started reading this book, and I got more and more excited as I went along. Things that I'd had kind of a vague gut feeling for were really precisely laid out in structured design. I thought, okay, this is great stuff. I'll be able to explain this. I went to UPSLA. I sat on the panel. Ed, who is sadly passed now, but Larry's still around, were gracious and funny and insightful. And I thought, okay, I take a vow now to bring this material to a modern audience. The book's difficult to read. The examples are about paper tape and magnetic tape, and should we use higher level languages, or is everything always going to be written in assembly language? So that doesn't reach a modern audience. I thought, okay, I will explain this to a modern audience. That was in 2005. I tried. I realized I couldn't really explain it. I tried some more. I found some better explanations for some stuff. I tried some more. life intervened. I went to work to make a living, but I kept at it. I kept trying to bring that material forward to a modern audience. And I particularly stuck on the definition of cohesion and why it mattered. Um, and it wasn't until, let me see, this has got to be 6 years ago now. So 2019, pre-COVID, boy, there's a turning point in everybody's life. I realized I had 2 weeks. I had 2 weeks unexpectedly free, and I thought I'm going to write as much of this book as I can in 2 weeks. And so I sat down to write, and as I typed, the first words off of my fingers was, software design is an exercise in human relationships. And I thought, whoa, no, 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 no. Finally, I'm talked a lot about extreme programming and now forest and desert and a lot, very people-y topics. Software design, that's a purely technical topic. I want to talk about coupling and cohesion, and I want to talk about power law distributions and preferential attachment, and finally I get a break from all of this human stuff, which is terrifically important and also very difficult for me. But no, the more I thought about it, the more I realized no, software design is an exercise in human relationships. You can write the most beautiful, modular, duplicate-free code in the world, and if you anger your teammates in the process, they're not going to use it. They're going to change things that you didn't want changed, and you're going to get frustrated, and the whole thing is going to go down in that familiar spiral. But okay, well, at the same time that we are talking about a human, social, tribal process, there are technical factors that drive that process, and those technical factors seem to be ignored by many of the people who talk about software design. So let's talk about both of those. And the result of that was a book called Tidy First, ? That came out 2 years ago now. I'm now working on the sequel to that called Tidy Together. And what I want to do today is talk to you about a central observation I made working on the sequel that didn't make it into the first book. And that's this principle that separates, it seems to me, the ways that I talk about software design and the ways that I hear other people talking about software design. And that is this principle that software is grown and not assembled. So back to Jordan and Constantine, the basics of the forces that are driving software design. One of the observations in that original structured design book, I call it Constantine's equivalence. And it goes like this. Back then, early 80s, when I was coming out of college, there was this observation that we were spending 60% of the development budget on maintenance. And of course, if you build a car and it requires more costs in maintenance than it did in manufacturing, something's wrong with the car. Something's wrong with that process. But in software, people were up in arms. Well, we have to get that maintenance cost, relative maintenance cost, down in order to reduce the cost of software. And Jordan and Constantine's observation was, No, this is actually okay. And in extreme programming, we talk about this. We say instead of 60% or 70% of the budget spent on maintenance, how can we get 99% of the budget spent on maintenance? We'll get this stuff into production as quickly as possible, and then all of the time we're going to spend, all of the money that we're going to spend is going to be spent on maintenance. We have something in production, we add features to it, or we improve its structure. Anyway, so Constantine's equivalence goes like this. The cost of software, if we want to reduce the cost of software, the cost of software is approximately equal to the cost of changing the software. There's this little period at the beginning where of initial development, but who cares about that? Most of the time, most of the money, most of the energy is going to be spent on making changes to software that's already working, already generating value. But not all the changes are the same. If you look at the cost of the changes that you make to software, say you have 100 features and they all seem to be kind of the same size. We'll just start with that assumption. This one's going to cost one, this one's going to cost one, this one's going to cost two, this one's going to cost one, this one's going to cost three, this one's going to cost one. This one's going to cost 100. What? Like the features are all the same size. Why would the costs be so unevenly distributed? And yet that's the facts. If you go and look at the amount of effort that goes into each PR, you're going to see exactly that kind of distribution. Lots of little things and a few great big ones. And if you add up the few great big features that you implement, the cost of those is going to dominate the cost of the changes. So the cost of software is approximately equal to the cost of changing the software. And the cost of changing the software is approximately equal, excuse me, to the cost of those big changes, those jackpot changes. We pulled the lever on the slot machine and bing, 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 except in this case, it's bad news, not good news. So the cost of software is the cost of change, and the cost of change is the cost of the big changes. And here's where the analysis came in. What makes those big changes big? We said the features are all approximately the same size as we go along, but somehow the implementation of those features is very different. And when they looked at the changes that were big, what they noticed was they all had the same property. And that is that we make one change here, which means we have to make two changes. We have to change this and this. And we make this change, and oh, then we have to change those 4 things. And because we change that, you have to change 8 more things. And because of that, and because of that, and because of that. And that's the original definition of coupling. So the cost of software is the cost of change. The cost of change is the cost of big change. And the cost of the big changes is approximately equal to this propagation of change from one element in the system to another. That propagation of change is exactly coupling. So we can compress all of that and say that the cost of software is approximately equal to the coupling in the software. That was the original analysis, and that's where coupling came from. And that original definition is 2 elements are coupled if, with respect to some change, that part's important, if and only if changing one element implies that you have to change the other element. And so we could look at a whole system and look at all the elements in the system, say all the functions in the system, look at them pairwise and say, with respect to this particular change, will change propagate from this function to that function. So things like if I reformat the internals of a function, that is a change, but it's not coupled to anything else. Nobody else can possibly care about the internals of it. Or please, I hope nobody can care about the internals of a function. It's the whole point of an abstraction, is that the outside's smaller than the inside. So that's Konstantin's equivalence. The focus of software design then is learning to reduce coupling, except that reducing coupling also has its own costs. And so the cost of the software is the sum of the coupling and the decoupling. So we've programmed along for a while. We didn't know we were going to make this kind of change. Now we have to make the change, and we realize, oh, that's a change that propagates from here to here to here to here to here. And then we have a choice. Can we reduce the coupling and then make the change? That's that tidy first of the title of the book. Can we reduce the coupling and then make the change, or should we just make the change and it's going to cost a bunch? So that's the beginning of the philosophy, recognizing that what we're dealing with is the cost of change plus the cost of reducing change. And that's what we need to balance as software designers all the time. Here I am. I'm about to make this difficult change. Do I make the change easy and then make the easy change? Or do I just, as we'd say in American English, bite the bullet and just, okay, I have to go change 100 places, so I go change 100 places. Now, interestingly, augmented coding is going to change, it alters what sorts of changes are expensive and what sorts of changes are cheap. And, I've done a few hundred hours of augmented coding at this point, but that's not the point of this talk. That's a whole different set of topics, except to recognize that we are changing the landscape, the cost landscape of what we're doing is changing dramatically week to week. And we all need to be aware that that's true. And some of us who like trying the newest things are going to be experimenting with what exactly are the implications of that kind of difference. Okay, so that's the message of tidy first, that we have. We're trying to reduce the cost of software, which means we need to reduce the cost of changing software, except reducing the cost of changing software is itself an investment that needs to be balanced. And what comes out of all of that is a philosophy of, I've always been more successful when I operated with lots of feedback. I make mistakes. If you don't make mistakes, you don't need feedback, right? But if you do make mistakes, then being able to accept feedback and adapt to it becomes extremely valuable. And the more your software is changing, the more valuable it is to work in smaller and smaller steps. This is another parting of the ways with how some people think of software design. They think of software design as something that you have to do as early as possible, because changing the design is always going to be expensive. And in the empirical world that I'm talking about, we take exactly the opposite assumption, that learning is the most valuable thing that we can do. If we learn, we're going to produce software. But if we produce software, we won't necessarily learn. And so we should arrange software development in such a way that we learn as much as possible, which means we have to do a little bit and then look at how that went and decide what it is that we want to do differently as a result of having done that first little piece. Okay, so that brings us to tidy together. And the thing I love about writing is when something comes out of my fingers that I never would have said out loud. And as I said, that first phrase, software design is an exercise in human relationships, that was one of those surprises. I had no idea what it meant when I said it. But then I realized, no, this is powerfully true. What we're dealing with is a human enterprise with technical constraints, not a technical enterprise with human constraints. So I got the book out there. People read it. Some people love it. Some people don't. That's life. Some people found it helpful. One of the things that people found most helpful or most resetting, most different than the way they were thinking before, is the idea that value in software comes in two forms. The first form is the one that is easy to recognize. We have features. We have the behavior of the system. So if I have a system and it connects people's voice calls and we can bill for that, there's some costs, there's some revenue associated with it. It's a cash flow. And if we continue operating the software, like cash flow is going to continue for some amount of time at some rate. And we can use the tools of finance to understand how much that's worth. But now imagine I have two software systems. I have one software system that has a certain set of features that creates a certain amount of profit. And I have another software system, but the first one, I can't change it at all. That's the features are the features, and it's in COBOL, and nobody knows how to change it, and that's that. Poof. But I have another system that implements exactly the same features, and I could change it in any number of different ways. We have the tests, we have the original team, we're working in a modern language, whatever. So I can change this one all kind of different ways, but the feature set is exactly the same. The customers are exactly the same between the two. Which one would you pay more for? You pay more for the one that can be changed. Why? The cash flows are the same. It's because the options that are embedded in that, along comes a new customer and they say, okay, well, I want this, but you need to change this and this and this. The original system, we just have to say, no, we can't do that. But this second system, we can say, no, that, yeah, we're happy to accommodate your wishes. So that optionality, if we look at financial markets, options are a thing. They trade for a price. We can evaluate that price. We can look at what makes options more valuable. And in particular, the more volatile the market, the more valuable an option is. So usually people say, well, if I could just pin down the requirements, if the requirements didn't keep changing, then I could get my software done. To which, in the empirical world, we say, no, that's backwards. I want an environment in which requirements are changing wildly, because that's what uh, emphasizes the value of optionality. So we can look at the features of the system and the options in a system as both being sources of value, and we could choose to contribute to one or the other or both. Now, it's very difficult, I think, impossible, probably impossible, to really add a feature and add options at the same time. So I don't even try. But I have this diagram. I'll try and reproduce it for you alive here. If we look at the value of a system, and the features are on one axis, and the options are on the other axis, then we can talk about the trajectory through this space. So we start out with a bunch of options. You know, we could implement anything. That's fine. And then we implement the feature, and in the process, necessarily we reduce our options somewhat. I mean, backwards compatibility, for example. Well, now that we have this implemented, we have to keep it running. Okay. So I can't just do anything I want. I would have to throw everything away, go back to zero on features, if I wanted to just throw everything away. But then the temptation, because features are so visible, the temptation is to go ahead and implement the next feature. But the more that you burn your options, the faster they disappear. Now, back to my earlier conversation about coupling, it's exactly the accumulation of coupling that reduces your options. And then eventually, adding features goes slower and slower, and then you're out of options. And then people do a little bit of work to restore options, and then they burn them implementing a little feature, and then they restore options. And that's the common trajectory. Now this is the trajectory whether we're talking about purely human developers or augmented developers, human plus genie development. That same trajectory is kind of the natural trajectory because the features are so visible. They're easy to count, they're easy to identify. That optionality, does it really exist? It's kind of a matter of opinion, but also not so much. And I've written books about that too. So the alternative to that trajectory, which looks kind of hopeless, like this, we're just going to drive this system into a state of anarchy and then it'll never recover. The alternative goes like this. Sure, you implement a feature, you burn a little bit of options, but then you have a choice. Do we just rush to the next feature, or do we spend a period adding to the options, reducing coupling, refactoring, tooling, simplifying, eliminating accidental complexity, teaching more people about the system? Those are all things that increase our options, even though they don't make any progress on features. And that's that little vertical piece there, that's exactly tidy first. But you can also tidy after. I implement a feature, I don't like it, so I clean up before I start the next thing. I can do that, or I can wait. I'm about to start a thing. It's a little bit ugly, so I tidy before I start. And that's legit too. But in both those cases, we're not making feature progress, but we are making options progress. And then we can implement the next feature. And then we can add to the options. And then we implement the next feature. And then we add to the options. And that's the trajectory that I'm advocating, that I try and practice, is one in which we're continually investing in the structure of the system to increase its optionality. We're not just on that feature hamster wheel, trying to get the next feature, the next feature, the next feature, and then you realize, oh, they're taking longer and longer, and they matter less and less. That's what I'd like to avoid. The thing I'd like to emphasize about this upper trajectory is that if I don't look at all of what's going on during development, all the details of what's going on during development, it looks like I have a system in which the features are improving day to day and the optionality is improving day to day. That's what I want. I call this the good news factory, where usually software development is full of bad news. You know, it's like, how long is this going to take? Oh no, and then a deadline, and no, it's not gonna, it's just bad news, bad news, bad news. And my goal is to have a good news factory instead of a bad news factory, where somebody comes and says, I sure wish the software could do this. And you say, well, actually, that's easy. Oh, really? Okay, well, we'll do that. The cost of that, though, is those periodic pauses in features to add options. And that's the topic of the tidy books, is what kinds of things do we do to add options by improving the structure of the software, and how do we continue doing them in the face of pressure, in the face of changes to the people on the team, in the face of expansion of the team, shrinkage of the team, people coming and going. And we'd like to be able to continue to make changes. So, where are we now? We've got coupling. We have the cost of softwares, the cost of change, which is equal to coupling plus the effort that we make to decouple. And we have the value of software coming from the features plus the value of the options for all the changes we could make in the future. Which brings us to this basic philosophical disagreement that I have with at least some people who write about software design, which is that software design is treated as an assembly process. We go out, we make all the pieces, we put them together, and now we have a piece of software. And I think that there's lots of ways to say this, and lots of people have said it before me, that ignores how software actually gets written and how software should be written. So there's John Galt is a thinker in systems design. And he says a large complicated system is always seen to have grown. A large complicated system that works has always grown from a small simple system that worked. And I think that's as good a summary as any of when I'm talking about software is grown and not assembled. That's exactly what I'm talking about. That the most efficient and effective way to get a large, complicated working system is to start with a small, simple working system. You know, cells, when you grow a body, you don't go, okay, I'm going to outsource the skin cells over here, and the bones are going to go over there, and the hair is going to go there. Well, eventually it goes away, but that's a separate set of problems. Teeth. Who's our teeth manufacturer? All right, everybody build so it goes really efficiently, and then we're going to pull everything together and we're going to assemble a human being. No. Nature operates by mitosis. I have a cell, it gets bigger and bigger, gets kind of uncomfortably big, and then it splits. And if you want to go down that rabbit hole, it's absolutely fascinating how it splits, and there's still aspects of that we don't understand, but it's a cool process. But now you have two cells, and those cells begin growing, and each of them gets uncomfortably large, and then they split and split and split and split. So the visualization that I use is software should grow like a tree grows. You don't go make a whole bunch of leaves and a whole bunch of roots and you put it all together. You start with one cell, and that cell splits and differentiates, and the one on top becomes what's going to be the trunk and the branches and the leaves, and the one on the bottom says, oh, I'm going to be more root-like, and then that splits, and the top one splits, and the and then eventually you have a big tree. And the objection to that is always, well, that's so slow. But compared to what? There's another process where, yeah, we go and make all the parts and we're just going to put them all together. This is divide and conquer. Sure, that sounds good, but it leaves out the hard part, the risky part, the part that we don't know enough to do, which is we're going to have to integrate those things when we're finished. So it's not divide and conquer, it's divide, conquer, and integrate. And that integrate step is complicated. It depends on us having done a good job of dividing in the first place. And we don't know how to divide. We don't know how at the moment, that's early moments before we have experience, we don't know how to divide so that we can integrate, because the details are going to matter a lot. So any design process that's based on divide first and then conquer is, in my experience and from my perspective, is just doomed. And here's the thing, it doesn't really buy you that much. This conquer and then divide, conquer and then divide, conquer and then divide process lets you accommodate the feedback that's coming in about both the external world, what features really need to be implemented, but also the internal world. How best can we structure this software? We can learn as we go along, oh, this set of attributes really doesn't interact with this set of attributes. There's no coupling between them. We can put them in separate places, which is a good thing to do, because then I can deal with this one as separate from that one. But I didn't make that decision up front. I looked at the software and how it was changing in order to recognize what I should do to split it. I have a project. I wanted to see if me augmented with Genie could write library quality software. So I picked in Rust, language I didn't know, I picked a data structure, a B tree. And there's a variant of the B tree called the B plus tree I could go on and on and on about this, but it's a lot of fun. And where was I going? Ah, yes, the grow like a tree grows. So I implemented this fairly complicated data structure, and it was all in one file, one big lib.rs file. And people were like, oh, well, don't you know about modularity? I'm like, yes, I know about modularity. I just don't know yet. I don't know how this wants to split up so that separate things are separate and together things are together. Because you'd like things that change at the same time to be conceptually close to each other, and you'd like things that don't change at the same time to be separate so you don't have to deal with them at the same time. So I went a long ways into implementing something that's functionally correct. I did a bunch of performance tuning, and then I could see, oh, I see the different operations on the map: get, insert, delete, iterate. That's the natural separation. And so I was able to create modules where all the get stuff was in one place, all of the insert stuff was in another module, all the delete stuff was in another module, all the iterate stuff was in its own module, and then they all relied on a common set of utilities to navigate the tree. But that moment of modularization came very late in the game compared to how a lot of people would do it. A lot of people would think, well, what should the modules be, even before they have anything working? And I think just the opposite. I want to I want to develop a practice that lets me continue making design decisions as I go along. And then that moment of modularity is exactly one of these big jumps. You know, I went along, I implemented some features, I fixed the design somewhat, I implemented some features, and then, oh, here's where the modules go. And as soon as I do that, I have more options for changing the software than I had before. I can even replace one of those modules with a different implementation of the same functionality without affecting any of the rest of the system, which is not something I could have done before the modularity. But I didn't know where the natural cleaving lines were in the software before I'd gotten a bunch of software implemented. So that's what I want to, oops, almost lost the pen. That's what I wanted to talk about today, that software should be grown and not assembled. As tempting as it is to divide and then conquer, that integration step is always going to be more expensive than we thought. And when the integration blows up, because it's exactly one of those jackpot moments, it's going to be extremely disruptive. But you don't have to live with that. You can grow and then divide. You can grow your software like a tree grows. You'll pay some price as you go along, but that's the insurance premium to make sure that you never are in a situation where you have a big integration that just goes really, really badly, because you've been integrating as you go along. Now, you can look at extreme programming and what I would now call the forest style of development as an application of that principle to every decision possible in software development, whether it's team composition or planning or road mapping or implementation or operations. It's the deferral of decisions until you have the information necessary to make the decisions. And yeah, it's not easy. It's not predictable. in the micro. It is very predictable in the macro, though. So, yeah, that was my message today. Oh, I have a few things. So, number one, start small. It's okay. You can start with one test. Try it. Try the experiment. Okay, I got 20 things I need to do. I have to design for all 20. Okay, well, maybe just design for 10. The 10 you're going to implement later, just don't worry about it. And then see if that goes better. And if it does, then design for 5 and 3 and 2. And just if you, how far can you push that process? How, if you have this sawtooth, if you get build your process to achieve that sawtooth, how small can the teeth be? And my answer was one test case at a time. You find your own answer, but do try the experiment. How small can you make it? The second thing to do is maximize feedback. So if you ever find yourself making 2 decisions in a row that are rest on unproven assumptions, how can you slice it? How can you rearrange the process so that you can get feedback on one of those assumptions before you have to get feedback on the next one? That itself is an intellectual game, kind of puzzle solving game, to say, how do I reorganize this project so that I get feedback sooner, as opposed to, let me show off my planetary sized brain by doing everything all at once. Kaboom. And the last one is to separate the implementation of features from the improvement in optionality. As I said earlier in the talk, I don't think that it's possible to effectively add a feature and improve optionality at the same time, at exactly the same time. Now, if we go from the outside, it may look like we're adding features and options at the same time, but inside we know that we're not. That my pappy's advice to me the first day I started programming, he said, make it run, make it right, make it fast. And I was like 12. I had no idea what he was talking about, but I kind of have spent the rest of my life pursuing exactly that. How do I separate the make it run from the make it right? How thoroughly can I make that separation? And then how short can I make the iterations so that from the outside it looks like I'm making progress on both dimensions at the same time, even though internally I know here's a new test case, it passes, then I refactor. Then there's another test case and it passes, and then I refactor. That's that kind of separation between the two that I was talking about. With that, wow, 50 minutes blazed by for me. I hope it did for you as well. And there was a mention made earlier about questions. I didn't have a chance to talk to the organizers about exactly how this was going to get put together. So if there are questions that came in, I'd be glad to answer them now.
Yes, Ken. Thank you for so insightful talk. I will give you some questions from the audience. I will just read them for you. And yes, thank you for your book and for your thoughts. I think that I'm following maybe the I'm totally agree with mostly all concepts of your book of extreme programming, and I really like it too much. And now we have some questions from our audience. It seems that you explained strategy in general, and who is responsible about the solutions from the beginning? software architecture, CTO, solution architect, developers, or maybe someone else?
A great question. There's there are conflicting incentives. So an architect would like to have the architecture be smooth, clean, not give bad surprises. The temptation then is to try and make the architecture decisions early so that you won't have any bad surprises. And my observation is the earlier you make those decisions, the more likely it is that you're going to get bad surprises. The challenge here as a senior developer, somebody with wider responsibility, the skill is to leave your all of your techniques. You have a big bag full of techniques that you carry around, but don't pull them all out at the same time. Say, now it's time to add event sourcing. Now it's time to add observability. Maybe that one comes earlier, but some observability, not observability of absolutely everything. That willingness to say, okay, this is a problem, but it's not a big enough problem yet to address it, frees you to create software, create feedback, and have macro optimization. That said, it's a really hard thing to do as a senior because you just see, oh, this is going bad, and I just know what's going to happen next. So let me avoid the problem altogether. I would say for senior leaders, setting vision and not intervening except occasionally. Every once in a while, you got to kind of smack it back on track. But for the most part, you let the team learn. And then comes that teachable moment when they can learn something big and you can pull out one of your bigger tricks. And that feels good. But that doesn't mean that you should have done it sooner. So I would say setting and maintaining a consistent vision is the job of senior leadership, and observing when there are moments to those one is this one of those rare moments to intervene.
Yes, I didn't catch the last thing, but hope you answered the question, and thank you
I
for
hope so
that.
too.
Yeah, thank you so much. And also, I have a little, I have not a little, it's really philosophical question and about obviously AI. As for me, pair programming was really revolutionary. Just to have two people around the one monitor and maybe in offline, in online world as well. And do you see AI copilots as a replacement of a partner or as a new kind of partner in the pair? So, what do you think about AI copilots and wipe coding with
Uh,
AI,
uh,
reviewing the code?
uh, yeah, replacement, hell no. This is a human process. We need to build and maintain relationships with the humans. I use the term augmented coding very specifically to put the human at the center of the process. Now, most of the time that I'm doing augmented coding, there isn't another person there, but I wish there was. Um, the experiments I've had with two people and one genie, I call it the genie because it grants your wishes, but it's not really what you asked for. Um, the times I've had two people and one genie, it's actually kind of nice. You have plenty of time to talk. You talk over what's the next prompt. You type it in. You're watching the progress. But now you're like, well, how'd that go? Are we doing the right thing? Those are the kind of conversations that happen during pair programming. But because the Genie is so slow compared to just raw typing code in, you have to be attentive all the time when you're typing code in. With augmented coding, there's you put something in and it's a minute, it's 3 minutes, whatever, time to get a coffee, time to have a chat. I think it's possible to have a more human process with augmented development than it is with just a raw IDE. That said, the tension is always to make it less human. All right, so I'm pair programming with the Genie and that's just as good. No, it's not, because the you're not building the relationships, you're not sharing the success, you're not both learning at the same time. Somebody says, hey, wait a minute, is there another way to implement this? Okay, so maybe you can ask the Genie that kind of question. That's something I love about it, is that I see some construct in Rust that I've never seen before, and I say, "Oh, what are the two ampersand single quote? What does that mean?" And it says, "Oh, well, that's a da, 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 da." I'm like, "Oh, cool! I can learn faster, but I have to take a pause to learn," and that's exactly that sawtooth. That's one of the things that you can do in one of these vertical moments where you just say, "Oh, why'd you do it that way? What are three other ways we could have done it? What is the implication of that? What does that introduce coupling? What's this language idiom? I don't. We have this endlessly patient tutor. We can use it as a tutor to help people learn, as opposed to just pretending it's this machine and I stuff prompts into and code comes spewing out. Boring.
Yeah, I can't I really get it, and I think that there is also a lack. Yes, it's really really great answer, and just I have another thought about it. What do you think in the new modern AI era, soft skills are becoming even more important than hard skills? Uh, yes, yes, yes,
Yeah,
obviously. Also,
yeah,
uh,
because
so, so,
because they have more leverage. If
mhm.
you and I have a conversation and I say, "Hey, I'm worried about this," and you say, "Oh, yeah, I was worried about that too, but I didn't want to bring it up," and we realize, "Oh, no, this is something we have to deal with." We turn to the Genie, we deal with it right now. That conversation between us, where we were vulnerable with each other, becomes much more highly leveraged than if we had that conversation and then we had to go and implement something and it took us 12 hours or whatever. If we can have the conversation and then deal with the issue right now and have it be completed, the conversation becomes so much more valuable.
Yes, so totally agree with you. And just maybe we are run out of the time, but I think that the last question is also about AI. So, how is AI changing their software development? Uh, was it becoming more just can you share your thoughts about this? How to use AI in a proper way to build easy maintainable systems? Is it possible to do it with AI?
Yes, it's possible. And so the short answer is nobody knows yet.
Mhm.
So if somebody confidently says, "Here's how you develop with AI," then they're definitely oversimplifying. There, I was going to say something nastier. They're definitely oversimplifying because it's changing all the time. We don't know what the implications of that are. If you're the kind of person who's excited by a lot of change and a lot of unknowns, the way I am, dive in and do it. Um, there are certain principles that are going to hold, like this sawtooth. That I don't see that changing anytime soon. But what exactly that looks like, and do you put it in the system prompt, or does it go in the pre-commit hooks? Who knows? Everybody should be trying everything in community, talking to other people who are also trying everything so that the good ideas spread as quickly as possible. In times of great technological change, like we're seeing right now, that's the best that you can do. Everybody tries everything and talks as much as possible to everybody else. That's what's going to get us to the next set of understanding how best to use these tools.
Yes, get it. Thank you for your thoughts. Thank you for your answers, Kent. You're more than welcome on our conference in Ukraine. Thank you once more time for your time.